These observations reveal a complex region filled with galaxy clusters, superclusters, and massive structures, including the Norma cluster, AEL 3627, one of the most massive galaxy clusters nearby and a major component of the Great Attractor.
The Great Attractor is not a single object, but a gravitational focal point formed by the combined mass of numerous galaxy clusters, dark matter, and gas. It acts like a cosmic drain, pulling nearby galaxies and clusters towards its center.
Our own local group, which includes the Milky Way and Andromeda galaxies, is part of this large-scale flow, moving at hundreds of kilometers per second towards this gravitational hub. However, the Great Attractor itself is part of an even larger structure.
Further studies have revealed that it lies within the Laniakea supercluster, an enormous network of galaxies spanning over 520 million light-years. Laniakea encompasses the Milky Way and several other galaxy groups, all gravitationally bounded and moving toward a common center near the Great Attractor.
This supercluster redefines our cosmic neighborhood and highlights how gravity shapes the universe on colossal scales. The Great Attractor's discovery reshaped cosmology by showing that the universe's structure is hierarchical and anisotropic. Matter isn't evenly distributed, but clumps together in webs, filaments, walls, and voids.
It also revealed that the universe is dynamic, with galaxies flowing along gravitational pathways rather than remaining static. Yet many questions remain. The exact nature of the mass concentration responsible for the Great Attractor is still not fully understood.
Dark matter, which makes up most of the universe's mass, plays a critical role, but is invisible to telescopes. The visible galaxy clusters account for only part of the gravitational pull, suggesting a large amount of unseen matter is concentrated in this region. Furthermore, more recent observations have uncovered what's called the Shapley supercluster, an even larger mass concentration located about 650 million light-years away. Some scientists suggest that the Great Attractor is only a local gravitational dip within a more extensive flow toward the Shapley supercluster.
This hints at a cosmic landscape of overlapping gravitational influences that guide the motion of galaxies over billions of light-years. Understanding the Great Attractor is crucial for measuring the velocity field of galaxies and refining models of cosmic expansion. It also helps calibrate the distance ladder, the set of methods astronomers use to measure distances in the universe by accounting for peculiar velocities caused by gravitational pulls, which can distort redshift-based distance estimates. In practical terms, the Great Attractor influences the cosmic microwave background CMBB through effects like the kinematic Sun-Zeldich effect, where galaxy clusters moving through the CMB imprint subtle temperature fluctuations. These observations provide independent evidence of large-scale motions consistent with the Great Attractor's pull. The search to map the Great Attractor continues with new instruments, including the Arosita X-ray telescope and surveys like the Dark Energy Survey, DEES, which aim to better resolve the hidden structures behind a zone of avoidance.
As we peel back layers of dust and gas obscuring our view, we expect to uncover more about the composition and extent of this gravitational giant. Ultimately, the Great Attractor is a cosmic reminder that galaxies are not isolated islands adrift in space.
Instead, they are part of a vast cosmic dance choreographed by gravity on unimaginable scales. The invisible hand of the Great Attractor guides this dance, pulling galaxies together, shaping the architecture of the universe, and reminding us of the hidden forces at work in the cosmos.
In July 2007, astronomers analyzing old data from the Parkes Radio Telescope in Australia discovered something unexpected: a powerful millisecond-long burst of radio energy that had originated from deep space. It was extremely bright, incredibly brief, and came from well beyond the Milky Way.
That first detection was later called the LoRa burst, and it marked the beginning of one of the most puzzling modern mysteries in astrophysics: the discovery of fast radio bursts, or FRBs. At first, these signals seemed to be one-time events.
FRBs appeared randomly in the sky and then disappeared, often without warning or any repeated signal. They came from all over the sky and had no obvious pattern. That alone was strange enough. Radio pulses from outside our galaxy, lasting just a few milliseconds, yet powerful enough to release as much energy in that instant as the sun does in a day. For years, astronomers wondered whether these bursts were caused by neutron stars, black holes, colliding objects, or even some unknown kind of astrophysical explosion. Then something changed. In 2016, astronomers using the Arecibo Observatory detected a signal known as FRB 1211102.
And this one repeated. It was a breakthrough. Unlike other ERBs, which were seen only once and then never again, FRB 12112 kept coming back. Dozens of bursts were detected from the same point in the sky.
This proved definitively that at least some ERBs are not cataclysmic one-time events. Whatever was producing these pulses wasn't being destroyed in the process. It was something persistent, repeating, and stable. The source of FRB 12112 was eventually traced to a dwarf galaxy more than 3 billion light-years away. This galaxy was small, low in heavy elements, and had signs of ongoing star formation. The precision localization achieved using interferometry with telescopes like the Very Large Array, VLA, allowed scientists to rule out many Earth-based or local sources of interference. This was not noise or a glitch. It was genuine extragalactic radio emitter of unknown origin.
Since then, many more repeatings have been found. Some, like FRB 1809 Monstist JO month date plus 65, display regular patterns. In this case, the bursts followed a 16-day cycle active for 4 days, then silent for 12, and then repeating.
This rhythmic behavior hinted at a celestial engine with a clock-like mechanism, possibly a rotating neutron star, a binary system, or something even stranger. Theories for repeating FRBs vary. One idea is that they're caused that magnetars, highly magnetized neutron stars.
Magnetos can produce sudden outbursts of energy when their magnetic fields rearrange or their crusts crack under pressure. In 2020, the Magneta SGR 1935 plus 214, located within our own Milky Way, emitted a short radio burst with FRB-like characteristics, lending credibility to this theory.
However, the burst was far less energetic than the extragalactic FRBs, suggesting either a different mechanism or that only the brightest magnetoflares are detectable at long distances. Other ideas include interactions between neutron stars and black holes, collisions of compact objects, or even exotic physics such as cosmic strings or dark matter interactions. More speculative ideas suggest technological sources, advanced civilizations using radio bursts as beacons or propulsion systems. While there is no evidence supporting the artificial origin theory, the regularity and intensity of some RFRBs make them stand out from other natural signals. What makes FRB 121102 especially intriguing is its dispersion. As the radio waves travel through space,
lower-frequency components are delayed more than higher-frequency ones, a signature of traveling through ionized plasma. This delay gives astronomers a way to estimate how much matter the signal passed through, effectively making cosmic probes of the intergalactic medium.
The more dispersed the signal, the farther it likely traveled, and the more it tells us about the invisible matter between galaxies. Some FRBs, like 12101 Non-2, come with additional clues. The bursts are highly polarized, meaning the radio waves are aligned in a particular direction. This suggests the signal passed through a strong magnetic field, possibly near a black hole or inside a supernova remnant. In fact, FRB 121 Norman 2 appears to be located in a star-forming region within its host galaxy, perhaps close to a young supermassive black hole or a dense cluster of neutron stars.
As of now, astronomers have cataloged hundreds of FRBs, with dozens confirmed to repeat. However, not all repeaters behave the same. Some emit frequent bursts, sometimes minutes apart. Others go quiet for weeks or months. Some are bright, some are faint, some are localized precisely.
Others are still poorly understood. The diversity suggests that FRBs may not come from a single type of object or event, but rather represent multiple astrophysical processes.
One of the most surprising discoveries came in 2020 when astronomers found a repeating FRB from within our galaxy. It was the first time an FRB had been detected so close to home, and it confirmed that at least magnetars can produce FRB-like signals.
This connection bridged the gap between exotic deep space bursts and known stellar remnants. Still, many questions remain. Why do only some magnetars emit FRBs? What explains the periodicity of certain repeating bursts? Why are some signals extremely bright and others faint? And perhaps most intriguingly, are we only seeing the tip of the iceberg, with the vast majority of FRBs going undetected due to instrument sensitivity, direction, or obscuration? New telescopes are helping to answer these questions. The Canadian Hydrogen Intensity Mapping Experiment, CHIME, has discovered hundreds of FRBs, revolutionizing the field by monitoring large swaths of the sky continuously. The upcoming Square Kilometer Array, SKA, is expected to detect thousands more and provide precise localizations.
These instruments will help astronomers map the full FRB population, measure their distribution, and ideally, determine their exact origins. The implications of understanding are broad.
Beyond their own mystery, they serve as tools for probing the structure of the universe, mapping cosmic magnetism, and studying matter that's otherwise invisible. Their dispersion measures can even help refine estimates of the cosmic baryon content, resolving discrepancies in how much normal matter we think exists versus how much we observe.
The fact that some FRBs repeat makes them especially valuable. Unlike supernova or gamma-ray bursts, which happen once and are gone, repeaters offer multiple opportunities to observe, study, and test theories. With each burst, they give astronomers a new puzzle piece, another signal from the depths of time and space, whispering a message that science is still struggling to decode. In summary, repeating FRBs are one of the most puzzling modern phenomena in astrophysics. They are brief, intense, and in some cases rhythmic. We know they're real. We know they come from far beyond our galaxy, and we know they carry valuable data about the cosmos, but we still don't fully know what they are.
And until we do, each repeating burst is a reminder. The universe is full of signals, and we've just started listening. Among the deadliest and most extreme objects in the universe are magnetars.
ultra-dense, hypermagnetized stellar remnants that defy comprehension.
These are a subclass of neutron stars, already some of the densest forms of matter outside black holes. But what sets magnetars apart is their mind-bending magnetic fields, the strongest known in the cosmos. Fields so intense they could theoretically strip electrons from atoms even from a distance of hundreds of thousands of kilometers. And yes, are powerful enough to wipe a credit card's magnetic strip from halfway across the galaxy. Let's start with the basics.
When a massive star, typically 10 to 25 times the mass of the Sun, explodes in a supernova, its core collapses into a neutron star, a dense object with about 1.4 times the Sun's mass, crammed into a sphere just 20 kilometers wide. The result is an object so dense that a single teaspoon of neutron star matter would weigh 1 billion tons. But a few of these neutron stars are born spinning rapidly and with unusually strong magnetic fields. These are the magnetars.
A typical neutron star has a magnetic field on the order of 10 to 12 GeV. For comparison, Earth's field is about 0.5 GeV. But magnetars crank that number up to an absurd 10 to 15 GeVs. 1,000 times stronger than a regular neutron star and 1 trillion times stronger than Earth's magnetic field. For scale, the most powerful magnets humans have built, like those in MRI machines or particle accelerators, barely reach 100,000 Gauss. At this intensity, the magnetic field alters the structure of atoms, flattening electron clouds and turning spherical atoms into elongated, cigar-shaped particles. The quantum vacuum around the magnetar doesn't behave normally either. Space itself becomes bordering, meaning light waves passing through are split and polarized by the magnetic field, an effect called vacuum biorigins, which has actually been observed around magnetars using optical telescopes.
So yes, that joke about magnetars erasing credit cards, it's rooted in real physics. A magnetic field that strong would induce electric currents in nearby objects, distort chemical bonds, and destroy electronics without ever touching them.
If you somehow brought a credit card within a few hundred kilometers of a magnetotar, its magnetic strip would be completely scrambled. If you brought yourself closer, well, your molecular structure would start to come apart long before you arrived. But magnetars don't just sit there quietly with their terrifying magnetic fields. They're prone to outbursts. As the intense magnetic field shifts and rearranges, it can crack the neutron star's crust, releasing huge amounts of energy in the form of gamma rays, X-rays, and radio waves. These are called starquakes, the cosmic equivalent of tectonic plates shifting on Earth, only made of super-dense nuclear matter. In 2004, a magnetar in our galaxy, SG 180620, located about 50,000 light-years away, released the most powerful flare of gamma rays ever recorded. The burst lasted just 2 seconds, but in that flash it released more energy than the Sun emits in 250,000 years. For a brief moment, it actually saturated satellite detectors and caused Earth's upper atmosphere to ionize despite being halfway across the galaxy. Had it been only a few light-years away, it might have wiped out Earth's ozone layer or worse. These flares make magnetars candidates for some fast radio bursts, those mysterious millisecond-long cosmic radio signals that repeat.
In 2020, astronomers detected an FRB-like burst from the magnetar SG 1935 plus 2154, located within the Milky Way. It wasn't as powerful as extragalactic FRBs, but it provided the first direct evidence that magnetars can produce FRB-like emissions. This made them one of the leading explanations for the mysterious signals we've discussed previously.
Magnetars are also linked to soft gamma repeaters and anomalous X-ray pulses, two types of strange objects that emit irregular high-energy bursts.
Initially, these were thought to be different categories of exotic stars, but we now understand they're likely just different observational behaviors of magnetars. How many magnetars exist? We've discovered only about 30 confirmed magnetars in our galaxy, but suggested models there may be thousands.
They're rare and short-lived in cosmic terms. The intense magnetic fields that define them decay over time, usually within 10,000 to 100,000 years, which is why we don't see them often. Once the field weakens, the magnetar may settle into life as a more typical neutron star or radio pulsar. So, how do they form? Magnetars are born in supernova explosions, just like regular neutron stars, but under highly specific conditions. If the progenitor star has the right mass, composition, and rotational speed, the collapsing core can amplify magnetic fields through dynamo effects during the explosion. The magnetic field strengthens rapidly and gets locked in as the neutron star forms. Interestingly, the birth of a magnetar might also explain some superluminous supernova explosions that are 10 to 100 times brighter than typical supernova. In these cases, it's believed the newly formed magnetar injects additional energy into the expanding debris, lighting it up far beyond what radioactive decay alone could achieve.
This is an area of active research, linking magnetophysics with some of the brightest events in the universe. Some magnetars may also form from neutron-star mergers, the same kinds of collisions that produce gravitational waves and collisions. In some scenarios, the merger doesn't immediately create a black hole, but instead forms a hypermassive magnetar, one that survives for a few milliseconds to seconds before collapsing under its own weight. During that brief window, it can release incredible amounts of energy.
The study of magnetars has pushed the limits of both observational astronomy and theoretical physics. These objects are natural laboratories for testing physics under conditions that can't be reproduced on Earth, including high-density nuclear matter, ultra-strong magnetic fields, and quantum effects in curved space-time. And yet, for all their violence, magnetos are invisible to the naked eye. If you looked at the sky where SG-18062 resides, you wouldn't see anything unusual.
But buried in that point of light is an object so extreme, so concentrated, and so volatile that its mere existence reshapes our understanding of what stars can become. In short, magnetos are like cosmic wrecking balls, small, dense, and dangerously magnetic.
They may not be common, but their influence, both physical and theoretical, extends across astrophysics. They represent the upper limits of how intense a magnetic field can be, how compact matter can become, and how violent the universe can get without collapsing into a black hole.
In space, collisions are not rare. But when most people imagine galaxies colliding, they picture a violent, catastrophic crash. Stars smashing into stars, planets torn from their orbits, and entire systems disintegrating. The truth is stranger.
Galaxies do collide, often spectacularly, but in many cases, they pass through one another like ghosts, continuing on their paths almost unaffected, at least in terms of direct impacts. It's one of the most counterintuitive realities in astrophysics. Galaxies collide without their stars actually hitting.
The reason lies in the sheer scale of galaxies. While galaxies can contain hundreds of billions of stars, those stars are separated by enormous distances. In the Milky Way, the average distance between stars is about 5 light-years.
So when two galaxies merge, the odds of any two stars colliding directly is incredibly low, like throwing two clouds of sand at each other from across a football field and expecting grains to hit. What does collide, however, is gravity and gas.
A famous example of a galactic collision is the pair known as the Antennae galaxies, located about 45 million light-years away in the constellation Corvus. These two spiral galaxies are currently merging.
And as they pass through each other, tidal forces distort their shapes, flinging out long streams of stars and gas into space. These tidal tails, shaped like antennae, are visible evidence of the gravitational interactions reshaping both galaxies.
While the stars mostly avoid direct contact, the gas and dust within galaxies does not. When interstellar gas clouds collide, they compress, heat up, and collapse, often triggering massive bursts of star formation. These are called starburst events, and they light up galactic mergers with new stars forming at rates much higher than normal. In the antenna galaxies, the collision has sparked the formation of thousands of new star clusters.
Over time, typically hundreds of millions to billions of years, the gravitational dance between colliding galaxies causes their orbits to decay. They spiral inward and eventually merge into a single, larger galaxy.
In most cases, the end result is not a bigger spiral galaxy, but an elliptical galaxy, rounder, more chaotic, and with less defined structure. The beautiful arms and disks of the original spirals are disrupted and rearranged by gravitational forces into a more uniform shape.
Our own Milky Way galaxy is on a collision course with its nearest large neighbor, the Andromeda Galaxy M31. The two are set to collide in about 4.5 billion years. And simulations suggest that they will pass through each other several times before finally settling into a merged elliptical galaxy, sometimes nicknamed Milcom-Dicka. Again, most stars, including possibly our Sun, will survive the process. The solar system may be flung to a different location in the new galaxy, but it's unlikely to be destroyed by direct collision. Galactic collisions also drive the growth of supermassive black holes at the centers of galaxies. When galaxies merge, the central black holes are pulled toward each other by gravity, eventually forming a binary black hole system. These black holes orbit each other, lose energy through gravitational waves, and ultimately merge in a violent event that may be detectable by future observatories like the Laser Interferometer Space Antenna, LISA.
The merged black hole ends up more massive and more active, sometimes powering a quasar. Observations from the Hubble Space Telescope and ground-based observatories have captured stunning images of galactic collisions in progress. In some, like NGC 4038 and NGC 4039, the antennae, the shapes are clearly distorted by gravitational tides. Others, like NGC 4676, nicknamed the Mice galaxies, show long tails of stars stretching out as the galaxies swing past each other.
These interactions help astronomers understand how galaxies grow and evolve. Galactic collisions are not just common, they're essential to how galaxies form. The hierarchical model of structure formation suggests that galaxies in the early universe began and grew small and larger through a series of mergers.
Many galaxies we see today are the result of multiple past collisions, their shapes and contents shaped by ancient encounters. Elliptical galaxies, in particular, often show signs of past mergers, distorted halos, shells, and star streams that are relics of long-dead companions.
Another well-known case is the Bullet Cluster, a pair of galaxy clusters that pass through each other. In this case, The galaxies themselves and their stars mostly passed through, but the hot gas clouds collided and slowed down, separating from the stars.
This separation of mass and gas provided one of the strongest pieces of observational evidence for dark matter. The stars and galaxies which were not slowed marked the locations of the total mass, which didn't align with the X-ray detected gas.
The extra mass inferred from gravitational lensing was attributed to dark matter. While collisions between galaxies may look serene from a distance, they can be disruptive for planetary systems.
As galaxies interact, their gravitational fields fluctuate, possibly perturbing star systems, stirring up gas clouds, and altering stellar orbits. These changes can trigger new star formation, but they can also cause instabilities in existing systems.
If a star passes too close to another during a galactic pass, it might disturb planets or send objects like comets into new orbits. But these effects are still rare and spread across immense distances.
Another surprising feature is that galaxies can collide and remain visibly separate for billions of years. The process isn't instantaneous, it's a slow gravitational wave. As they pass through one another, galaxies can be stretched, spun, and twisted.
But they can also continue on their paths and collide again later. This happens because of dynamical friction, a process where gravitational interactions with surrounding matter slow down massive objects. Over time, this causes the galaxies to settle into one combined system.
Mergers can also trigger active galactic nuclei, AGN. As the gas in colliding galaxies falls towards the central black holes, it heats up and emits radiation. In some cases, this results in quasars or blazars, some of the brightest objects in the universe.
So, while the stars pass through each other, the interaction of gas and gravity can light up the universe in dramatic ways. One final detail: not all collisions are between equals. Some involve large galaxies devouring smaller ones.
These are called minor mergers, and they happen frequently. The Milky Way is currently in the process of absorbing several dwarf galaxies, including the Sagittarius dwarf elliptical galaxy, which has already been torn apart and wrapped around the Milky Way in long streams.
These minor mergers are thought to build up galactic halos, enrich them with stars, and contribute to the complex structure we observe in galaxies today. In summary, galaxies do collide, and they often pass through each other without direct stellar crashes.
The collisions are slow, gravitational, and transformative. They reshape galaxies, trigger starbursts, feed black holes, and build the large-scale structure of the universe. They also remind us that space, while vast and mostly empty, is not static. Even the largest structures are in motion.
And over cosmic time, nothing stands still. According to modern cosmology, the universe is approximately 13.8 billion years old, a figure derived from measurements of the cosmic microwave background radiation, expansion rate, Hubble constant, and Big Bang nucleosynthesis.
So when astronomers find a star that appears to be older than that, something is clearly off. And that's exactly what happened with a star called HD 183, nicknamed the Methuselah star.
A star whose estimated age once appeared to be older than the universe itself. HD 140283 is located about 190 light-years away in the constellation Libra. It's a subgiant star, meaning it's in a transitional phase between a main sequence star and a red giant.
What makes it special is its extremely low metallicity. That is, it contains very few elements heavier than helium. In astrophysics,
Metals include all elements heavier than helium.
And stars with extremely low metallicity are considered population 2 stars, formed very early in the universe when only hydrogen, helium, and trace amounts of lithium were abundant.
The Methuselah star has less than 250th the iron content of the Sun, suggesting it formed from gas that hadn't been significantly enriched by earlier generations of stars. This alone hints at extreme age.
But the surprise came when astronomers tried to determine just how old it actually was. Using data from parallax measurements, spectroscopy, and stellar evolution models, astronomers in the early 2000s estimated HD 132 Freese's age to be around 14.46 billion years, with an uncertainty of plus 0.8 billion years. Even at the lower end of that range, it still pushed the limits of the universe's accepted age. At the higher end, it seemed to predate the Big Bang. This was not just a minor discrepancy, it was a major headache for cosmologists.
If the universe is 13.8 billion years old, nothing in it should be older than that. So how could this single star appear to defy that fundamental boundary?
The answer lies not in rewriting the age of the universe, but in re-evaluating the methods used to age-date stars. Estimating stellar ages is not straightforward.
It involves complex models of stellar interiors, nuclear fusion rates, opacity, mass loss, and chemical composition, all of which introduce uncertainty. For a star like HD Wanton's 283, even a small error in any one of these parameters can result in age estimates that are off by hundreds of millions of years.
One key variable is distance. Parallax measurements determine how far away a star is, which in turn helps determine its intrinsic brightness, a key input for age models. Early parallax data had large uncertainties. When the Hubble Space Telescope was used to obtain a more precise parallax measurement in 2013, the estimated age of HD 1402283 was revised to 13.7 billion years, with an uncertainty of plus 0.7 minus 0.17 billion years.
This brought the star's age just within the bounds of the universe's age, resolving the immediate conflict, at least statistically. Even with the updated age, HD 402283 remains one of the oldest known stars in the universe.
It likely formed just a few 100 million years after the Big Bang, possibly from the remnants of the very first stars, the hypothetical population 3 stars, which were massive, short-lived, and left behind only trace elements.
HD 132 US or 3 carries the chemical fingerprint of an early universe that hadn't yet been enriched by multiple cycles of star formation and supernova explosions.
The Methuselah star is important because it serves as a time capsule, preserving conditions from the early universe in its composition and structure. Its very existence helps constrain models of galaxy formation, chemical evolution, and stellar nucleosynthesis.
It tells astronomers when certain types of stars could first form, how long it takes to reach different phases of stellar life, and how fast elements like iron and carbon build up in galaxies. It's also a reminder of the limits of measurement.
The older than the universe result wasn't a sign that the Big Bang theory was wrong. It was a reflection of how difficult it is to pin down age with absolute certainty. Astronomical data always comes with error bars.
And occasionally, those bars overlap in ways that produce surprising or seemingly paradoxical results. When measurements become more precise, those paradoxes often resolve themselves. But HDZ Thorn 283 isn't alone in stretching cosmic timelines.
Other extremely metal-poor stars have been found with estimated ages approaching or slightly exceeding the universe's age, depending on the model used. These include stars like BD plus 17 D3248 and HE 1523, both of which have extremely low metallicity and old age estimates.
These cases highlight how stellar archaeology complements cosmology. While observations of the cosmic microwave background and the large-scale structure of the universe provide one way to measure the universe's age, ancient stars offer a completely different method.
If their ages consistently exceeded 13.8 billion years, it might suggest a fundamental problem with cosmological assumptions, but so far most results are converging barely around the same timeline.
Another wrinkle is that the Hubble constant, the rate at which the universe is expanding, is itself the subject of debate. Measurements using the cosmic microwave background from the Planck satellite give one value.
Direct measurements using supernova and Cepheid variables give another slightly higher one. A higher Hubble constant would imply a younger universe, potentially reviving the conflict with the Methuselah star. This is known as the Hubble tension, and it remains one of the most active and unresolved questions in modern cosmology. So while HD 1283 may no longer technically predate the universe, it still occupies an extreme edge case, old enough to probe the earliest era of stellar formation, but close enough to the boundary of known physics to keep astronomers on the edge. It forces improvements in stellar models, challenges cosmologists to refine the age of the universe, and serves as a constant reminder that our cosmic timelines are still open to revision. In summary, HD 143 Intanu 283, the Methuselah star, doesn't actually break the laws of physics, but it came close enough to spark a serious re-examination of how we date stars and how we define the universe's history. It's a stellar anomaly that helped tighten science, refine models, and prove once again that even a single object shining quietly in the sky can push the boundaries of what we think we know. In the large-scale map of the universe, galaxies don't appear randomly scattered. Instead, they form a vast, intricate web of structure, an interconnected network of filaments, clusters, walls, and voids. Among these structures, one of the largest ever discovered is simply known as the Great Wall, but even that name doesn't capture the full scale of what we're dealing with.
A cosmic structure that stretches across 1.4 billion light-years, made of galaxies bound together by gravity into a massive spine-like ridge of matter. The discovery of the Great Wall began in the 1980s and 1990s as astronomers undertook massive redshift surveys to map the positions and distances of galaxies across the sky. In 1989, Margaret Geller and John Hushra of the Harvard-Smithsonian Center for Astrophysics revealed a striking finding from the CFA2 redshift survey: an extended region of space densely packed with galaxies forming a sheet-like arrangement.
This became known as the CFA2 Great Wall, or simply the Great Wall, the largest known structure at the time. Its length, about 500 million light-years, stunned researchers. But it was just the beginning.
Over the next decades, larger and deeper surveys revealed even more massive structures. One of these, found in 2003, was the Sloan Great Wall, a filament discovered in data from the Sloan Digital Sky Survey, SDSS. The Sloan Great Wall turned out to be roughly 1.37 billion light-years long, making it nearly 3 times the size of the original CFA2 Great Wall. It remains one of the largest coherent structures ever detected in the observable universe.
To understand what makes the Great Wall so remarkable, it helps to look at what it's made of. It's not a solid object. It's a galaxy filament, a thread-like formation composed of clusters and superclusters of galaxies arranged in a relatively narrow band, but stretching over an immense distance.
Each cluster contains hundreds or thousands of galaxies. The entire structure includes millions of galaxies, all gravitationally connected and embedded in a web of dark matter and intergalactic gas. The scale is hard to grasp.
Light takes 1.4 billion years to cross the length of the Sloan Great Wall. That's about 10% of the age of the universe itself. If you could somehow observe the structure from outside, from a hypothetical point billions of light years away, the Great Wall would look like a cosmic scar etched across a huge region of space.
This raises a fundamental question. How do such large structures form? According to current models of cosmology, structure in the universe forms through a process called gravitational instability.
Tiny fluctuations in the density of matter seeded in the very early universe grew over billions of years as gravity pulled matter into denser regions.
Over time, this gave rise to the cosmic web, a sponge-like network of dense filaments where galaxies form, separated by vast empty voids. Simulations like the Millennium Simulation and more recent ones from the Illustris and Eagle projects reproduce structures similar in shape and scale to the Great Wall.
Although the very largest walls, like Sloan's, push the limits of what we'd expect, some scientists have debated whether a structure this large violates the cosmological principle. The idea that the universe is homogeneous and isotropic, the same everywhere on large scales.
But most evidence suggests that such structures can still emerge naturally in a universe governed by cold dark matter and dark energy. Still, the Great Wall blurs the line between structure and anomaly.
It is so massive, so extended, and so coherent that it challenges simple statistical explanations. Some astronomers even question whether it's truly a single object, or rather a chance alignment of several superclusters along the same line of sight.
The difference matters because if these kinds of walls are too frequent or too large, they could contradict our best cosmological models. Other superstructures rival the Great Wall in size, and some even exceed it, depending on how structure is defined. For example, the Hercules Corona Borealis Great Wall, discovered in 2013, has an estimated length of 10 billion light-years, making it the largest known structure in the universe by a wide margin.
However, the evidence for this wall is based on the clustering of gamma-ray bursts, and it remains a controversial finding. Many cosmologists remain skeptical, as such a massive structure would challenge the assumption that the universe becomes statistically uniform beyond certain scales.
Unlike a building wall, the Great Wall isn't static or unchanging. Galaxies within the structure are moving, evolving, merging, and forming stars. The wall itself will change over time.
Gravity will continue to shape it, pulling some clusters closer and possibly causing portions to collapse into even denser regions. Over tens of billions of years, dark energy will accelerate the universe's expansion and begin to tear these massive structures apart by stretching space itself.
Despite its scale, the Great Wall is not visible to the naked eye from Earth. No single telescope can photograph it in full, as its span covers too much of the sky and lies too far away.
It was only discovered by measuring the redshifts of hundreds of thousands of galaxies, converting their positions into a three-dimensional map. The wall revealed itself as a pattern in data, not in light.
Its discovery is a reminder of how much we owe to survey science. The painstaking work of cataloging objects across large parts of the sky.
Tools like the Sloan Digital Sky Survey, the 2DF Galaxy Redshift Survey, and now the Dark Energy Spectroscopic Instrument, DESI, continue to uncover ever more detailed maps of the universe, revealing that space is anything but empty and uniform. The existence of these giant walls also affects how we understand cosmic flows, the motion of galaxies under the influence of gravity. Regions near large structures like the Sloan Great Wall can have bulk flows where hundreds of galaxies move together toward a dense region.
These flows help test models of gravity, dark energy, and cosmic inflation, giving us tools to refine our understanding of how the universe behaves on the larger scales. In some sense, the Great Wall and its like represent the edge of our comprehension.
They don't break physical laws, but they remind us that the universe is structured, dynamic, and vastly more intricate than early cosmology imagined. The universe isn't just expanding. It's sculpting itself over eons into a web of matter and voids, with galaxy filaments as the skeleton. In summary, the Sloan Great Wall is one of the largest known structures in the universe. A 1.4 billion light-year filament of galaxies and clusters forming a kind of cosmic architecture. It's too vast to see, too massive to ignore, and just strange enough to keep scientists asking whether we fully understand what the universe is made of and how it all fits together. When we look out into the night sky, we're not just seeing stars. We're looking back in time. Because light travels at a finite speed, about 299,792 kilometers per second, distant galaxies appear not as they are now, but as they were when the light we're seeing left them. The farther away an object is, the older the light we receive. This simple truth leads us to one of the most profound boundaries in modern science, the edge of the observable universe.
The observable universe is the part of the cosmos from which light or any signal has had time to reach us since the Big Bang, 13.8 billion years ago.
But due to the expansion of space itself, that boundary is much farther than 13.8 billion light-years. In fact, the radius of the observable universe is about 46.5 billion light-years, meaning the entire visible sphere spans roughly 93 billion light-years across. Anything farther away than that, we simply can't see it, not because it doesn't exist, but because its light hasn't had enough time to reach us, and never will if expansion continues accelerating. This edge isn't a physical wall or boundary. It's a horizon like the one you see on Earth's surface. Just as you can't see beyond the curve of the Earth from ground level, you can't see past this cosmic horizon. It's defined by cosmic time and the speed of a light, not by any physical object. What lies at this edge? Not much, just the farthest photons we've been able to detect, the cosmic microwave background, CMB-BB. This faint glow of ancient radiation comes from a time about 380,000 years after the Big Bang, when the universe cooled enough for atoms to form, allowing light to travel freely for the first time. It's essentially the surface of last scattering, the most distant electromagnetic signal we can currently detect. Beyond that, everything is opaque to light. But we know based on models of cosmic inflation and the uniformity of the CMB-B that space doesn't just stop at the observable edge. It keeps going, possibly infinitely.
The observable universe is just a small patch of the entire cosmos, the part we're able to access with our instruments and current understanding of physics. The rest remains unobservable, at least for now, and perhaps forever.
What might be out there beyond our cosmic horizon? The best guess, supported by the cosmological principle, is more of the same. Galaxies, stars, clusters, voids, all governed by the same physical laws.
If the universe is homogeneous and isotropic on large scales, as suggest observations, then the regions beyond what we can see probably resemble what we do see. There's no reason to believe we're at a special location. But there are alternative ideas too.
Some physicists have proposed that beyond the observable edge, the universe could become radically different. Different densities, different cosmic histories, even different physical constants. And then there's the possibility of a multiverse.
That our observable universe is just one bubble in a vast cosmic foam of universes, each with its own laws, dimensions, or physical properties. What limits us from seeing farther is cosmic acceleration.
Due to dark energy, the unknown force driving the universe's expansion faster over time, most of the universe is receding from us faster than the speed of light. While that might sound like it breaks relativity, it doesn't.
Because space itself is expanding, not objects moving through space. As a result, many galaxies are already permanently beyond our reach. Their light emitted today will never reach us, no matter how long we wait.
This means the observable universe is shrinking in practical terms, not in size. The radius is still 46.5 billion light-years, but in what we can ever hope to interact with, more galaxies fall beyond our communication horizon every year.
In trillions of years, all but the closest galaxies will have disappeared from view entirely, leaving any future observers stranded in what appears to be an empty, static cosmos. That's the ultimate consequence of accelerated expansion.
Still, within our observable volume, we can study the structure of the universe in incredible detail. We see about 2 trillion galaxies, and thanks to instruments like the James Webb Space Telescope, JWST, we're now detecting galaxies that formed less than 300 million years after the Big Bang, incredibly close to the edge of the visible universe.
And as JWST and future telescopes probe deeper, they give us a clearer picture of what the early cosmos looked like. Star formation, the birth of galaxies, and the buildup of structure that would eventually shape the modern universe.
But even with this detail, there's a hard wall we can't break. We can never observe anything beyond the cosmological horizon, no matter how powerful our telescopes become.
No signal, no matter how energetic, can cross that boundary if it's been stretched beyond reach by space itself. The edge of the observable universe is a limit not just of technology, but of causal fundamentality. It also invites philosophical questions.
If there's more universe beyond what we can see, and all evidence suggests there is, then how much of it is there? Is it infinite? Is it curved or flat on scales we can't probe?
Are there versions of us out there in an unimaginably vast multiverse? Or is our universe a one-off anomaly? These are the kinds of questions that push cosmology into the realm of theoretical physics, areas where evidence is scarce. But reason and math offer guidance.
Inflation theory, the idea that the universe underwent a rapid exponential expansion in the first tiny fraction of a second, predicts that the universe could be much larger than what we can see, possibly infinite, possibly curved, possibly connected to other bubble universes.
In some models, inflation never stops entirely, spawning new universes in an eternal cascade, a process known as eternal inflation. But we can't prove it, not yet.
All our evidence comes from what's inside the observable bubble: the galaxies, the cosmic microwave background, the distribution of matter, all of it limited by the light cone that defines our cosmic reach. We can only infer what's outside based on what's inside.
It's a bit like trying to understand the shape of the Earth while standing on a hill and looking to the horizon. You can get clues, but you can't see the whole thing. One final twist.
The boundary of the observable universe is not the same for everyone. An observer in a galaxy billions of light years away would have a completely different observable volume. Their horizon would include galaxies we can't see and exclude some that we can.
In that sense, there is no single edge of the universe, only personalized horizons defined by location and time. Each observer in the universe has their own observable bubble. In summary, the edge of the observable universe is not a wall, but a limit.
A horizon that marks how far we can see, how far we can measure, and how far we can know. Beyond it lies a realm of unanswered questions. More galaxies, more matter, more space, and possibly much more mystery.
The universe continues past our vision. How far and how strange it gets remains one of the biggest questions in all of science.